first unit of this course is called the real line, or we could call it the real numbers. Okay, so calculus is in a sense the art of manipulating real numbers and doing everything you can do with them. Okay, and so during the course we'll learn to study functions of real numbers and their behavior, so that we can compute how a curve is varying, how it's changing, the speed is changing with the areas, things like that. So many things we can do with calculus, but the basic ingredient of all these things that we will do during the course are the real numbers. Okay, and we call it the real line because we can draw this. Let me draw it here. We usually draw the numbers in a line, so it's starting at 0. Okay, this goes positive up to plus infinity, and this goes negative up to minus infinity. Okay, and in this line we can write up any number that we can think of. Okay, but before we can get here, I need to introduce some properties of the real numbers, and also to talk about other number systems. Okay, so if you think about it, because I mean you've used real numbers before in high school, and you're used to this kind of decimal numbers, things like that, from your everyday life. So it seems like it's a natural thing, but it's actually not really natural. And the actual kind of definition of the real numbers took it was really defined in the end of the 19th century, early 20th century. Okay, so these properties were not really clear until 1 century ago, which is it's just crazy when you think about it. Okay, so in fact the only natural numbers, or the intuitive numbers, are what we call the natural numbers. Okay, and we'll talk about them later in this unit. And then so from them you can start building up more kind of intricate number systems up until you get to the real numbers, which we all know. So my interest here in this first unit is to show you what the real numbers are and what their properties are. And so in a sense I think this will not be new for you, because most of this you will have seen during high school. Maybe a couple of things I will make some emphasis on, and so that you will need to pay attention to it. But other than that, these are things that you already know. Okay, so it should be easy. But anyway, so don't take it for granted. Pay attention, because these things will be very useful, or it be the basis of the things that we will deal with in the rest of the course. Okay. Okay, so in order to do all these operations, at least calculations that we want with the real numbers, what we want is a system that has a series of properties that we can manipulate in a sense of, and in a series of ways. And in math, what we call a system like that is a field. Okay, so a field, okay, here field, okay, this is an algebraic structure, so you don't need to know about this algebraic, okay, structure. So you're not going to be mathematicians, so you don't need to really pay attention to this, but just so you know, okay, this is what this is called in math, algebraic structure. So a field is a set of elements. Okay, so a set of different elements, in this case numbers, that will have two different operations. Okay, the sum, okay, and the multiplication. Okay, and in order for the field to work as we want, or these two operations to work, we need to define some properties for them. Okay, and so the way we do this is we define the field, this structure, as in this way. So for all x, y, and z elements of the field, okay, the following properties hold. So first are the properties of the sum, and we call them addition. Okay, sum, addition, sum. The actions. So what is an action? So an action is kind of you could call it a hypothesis in a sense, or an assumption. Okay, so it's kind of assumption. So in math, when we're defining a system, we need to set up some actions such that we know how to deal with the system. Okay, so this is kind of the basic way we do things in math. Okay, so these things, these 4 axioms, are properties of a field that we kind of force into it, or we set up, and we don't need to prove anything in order to arrive at them. Okay, we assume these things are true from the beginning. Okay, so you could think, these properties are kind of obvious. Okay, for instance, so the first property of the sum is that it's commutative. Okay, so x plus y, it's equal to y plus x. Okay, and you can say, oh yeah, well, that's obvious. Okay, always the sum has to be commutative. But this is not true in general. I mean, so you could always define another operation, call it sum, without this property. Okay, and actually that's one whole area of math, is to deal with some operations that do not have this property. Okay, so let me think how to say this. So the thing is, these properties will feel very obvious to you, and I mean, when I started studying math as well, they felt very obvious to me. But the thing is, they're obvious because that's the way we deal with real numbers normally. But what I want you to realize is that you can actually define many other operations that will lead to different algebraic structures, and so the things that you can do with those systems will be different than the things that you can do with the real numbers. Okay, so now back to the real numbers. So we haven't arrived at the real numbers yet. So this is a general field. Okay, so any field, okay, has to satisfy these actions. Okay, so the first one is that the sum has to be commutative. Okay, x plus y is equal to y plus x. It has to be associative, which means that x plus and then parentheses y plus z is equal to parentheses x plus y plus z. Okay, again, this kind of seems obvious, but it's not. Unless you define it to be true, you could define a different sum operations without this property. Okay. Then the third property is that there is a zero. Okay, there's a number that we call zero, such that when you add it to any other number, you have the original number. Okay, x plus 0 is x. Okay, it doesn't matter what value you have for x, then you have the same number. And the fourth property, okay, is that each number x, there is what we call an inverse. Okay, for each x there is a number that we call minus x here, such that x plus this minus x is equal to 0. Okay, when you sum them, you get the zero element. Okay, and normally, okay, you'll see this is what we call x minus x. Okay, but in truth, we don't have an operation that's called subtraction. The subtraction is just summing the inverse of this number. Okay, so this is just like really math nitpicking in a sense, but it's important that you see where these things come from. Okay, so whenever I have an operation like this that has these 4 properties, we have what we call a group. Okay, a group is another algebraic structure. Okay, and in this case, it's a commutative group. And as I was telling you before, there's a whole area of math that deals with groups that are non-commutative. Okay, So yeah, don't worry too much about that. But so groups are the numbers that and the system of elements that fulfill these properties. Okay, so now the multiplication actions are kind of the same. The first, this multiplication has to be commutative. X times y is the same as y times x. Then x times y times z is equal to x times y and then times z. So this is associative. And then you have this unity. There's a number 1 such that x times 1 is equal to 1. And then you have the inverse again. So for x that's different from 0, there is a number that we call x to the minus 1, or we can also call it 1 over x, such that x times the inverse is equal to 1. Okay, or you could write it x divided by x. Okay, this is what we call division. Okay, so this is the reciprocal in terms of multiplication. So as you can see, these multiplication actions are very similar to this, and this means that this field is also a group for the multiplication. Okay, so a field has to be a group for the action, the addition, a group for the multiplication, and then you have two extra properties. Okay, these two guys that hold for the two. So they're a combination of the two operations. So the first one is what we call the distributive law. That means that x times the parentheses of y plus z is equal to x times y plus x times z. Okay. And then the last one is that 1 is not equal to 0. Okay, so the 0, okay, this 0 of the sum is not the same as the 1 of the multiplication. Okay, if that was the case, then the only set that fulfills these properties is the kind of trivial set 0. Okay, so we would have a field that's only the number 0. Okay, so in order for the field to be non-trivial, we call it non-trivial. Okay, non-trivial, then we need this property. Okay, so this is what it says here. Oh yeah, and just so you know, so whenever I write these brackets, so for instance 1, 2, 3, I'm denoting a set. Okay, so this is a set, and it's kind of the most basic structure of math. Okay, a set is just a list of elements. So this set contains the numbers 1, 2, 3. Okay, and that's it. They appear only 1, and so you will see these brackets appear over and over and over again during the course, because that's how we write things in maths. Okay. Okay, so now those are the axioms of the field. Okay, in order for us to do everything we want to do with the real numbers, we also need another other properties, which are the order axioms. Okay, so we want our field to be an ordered field. Okay. So in order for a field to be ordered, we need a new operation that we call like that, smaller or equal than. Okay, and it has these properties. Okay, so the first one is that x is smaller or equal than x, and we call this property reflexivity. Okay, so this is kind of, we assume this to be true for this operation. Okay, then if x is smaller or equal than y and y is smaller or equal than x, okay, these two things are true at the same time, then x is equal to y, and we call this anti-symmetry. Okay, property. And then finally, if x is smaller or equal than y and y is smaller or equal than z, then x is smaller or equal than z. Okay, and this is transitivity. Okay, these three properties define what we call partial ordering, or an ordering, just partial ordering. Okay, so whenever we have any operations just like this, or relation, and then we have these three properties, we can order the elements in our set. Okay, and the rest, and the fourth property, okay, what this does is it defines the total ordering. and it says that, you know, either x is smaller or equal than y, or y is smaller or equal than x. Okay, so that means that every number or every element in the set will be ordered. You can write them in order from the smallest to the greatest. Okay, and again, this is not obvious. For instance, many systems don't have a total ordering. So if you think about, you know, points in 2 dimensions, so if you think about the coordinates of a point, okay, x and y, so you can think of a set of points, x1, y1, x2, y2, x3, y3, and so on. Something like this. This kind of sets do not have total ordering. Okay, it's not. It's impossible to define an ordering such that these elements are. Well, yeah, that's wrong. It's not impossible to to define an order such that there is a total ordering. It's not. But the typical orders that order relations that we define are do not define a total ordering. For instance, you have let's see, 1, 3, and then 0, 5. Is this number smaller or equal than this, or is this number smaller or equal than this? Okay, so that the way we define smaller is that, you know, x1, y1 is smaller or equal than x2, y2 if x1 is smaller or equal than x2 and y1 smaller or equal than y2. Okay, but in this case, x2 is smaller than 1, but y2 is not smaller than y1. So this relation is not fulfilled. Okay, so if you define orders for this kind of order for 2-dimensional numbers, then you don't have a total ordering. Okay, I don't know if that was clear, but I hope it was. Okay, so just remember that not every ordered field has a total ordering. And then property 15, then you have what we call this compatibility with addition. Is that if x is smaller or equal than y, then x plus z is smaller or equal than y plus z. Okay, so this is again an axiom that we force into the relation. If we add anything to this side, then and we add the same thing to that side, then the relation is still fulfilled. Okay, and this will be very useful when we deal with inequations. Okay, so inequations are expressions of the form like this. Okay, so where this smaller or equal is involved, right? So this is an inequation. Well, they call it inequation because there are inequalities involved. And finally, so the same, the compatibility with the multiplication. Okay, so if x is greater than 0, so sorry, if 0 is smaller or equal than x and 0 is smaller or equal than y, then 0 will be smaller or equal than the product. Okay, so if x is a positive number and y is a positive number, the product of the two will be a positive number, right? So, well, this is the first hint of why we call the numbers the real line, is because now we have the order actions. We can order them, so we can put them in a line, and so we can put the smallest numbers to the left and the greatest numbers to the right, so that, you know, x1 is x1 is smaller or equal than x2, and x2 is smaller or equal than x3. Okay, but yeah, and normally we don't use smaller or equal than, we use smaller. Okay, so x1 is smaller than x2 and x2 is smaller than x3. But when is this true? Well, whenever x1 is smaller or equal than x2 and x1 is not x2. Okay, so these two imply x1 is smaller than 2. Okay, so then we have this smaller or equal, we have this greater or equal. Okay, so this is kind of the inverse. And then we have smaller, which is a smaller or equal and not equal at the same time, and then greater, which is greater or equal and not equal at the same time. Okay. And then, so we can, using these properties, so, once we have these properties, so from 11 to 16, and then before for the field actions, then we have all the elements we need for us to prove anything we need to prove about real numbers. Okay, so then we'll start dealing with that. So the first thing we proved, and so this is called the Law of Trichotomy, and this means that the Law of Trichotomy says that for every pair of elements x and y of an ordered field, any field, one and only one of the following relations hold. So it's either x is smaller than y, x is equal to y, or x is greater than y. Okay? So that means that now we have every element related to each other in this kind of way. Okay? Once we have, so if they give us two elements from this set, we can say they smaller than the other, equal or greater than the other. Okay, and just as an aside, this is called a proposition. Okay, so in math, whenever we prove a statement, okay, so a statement is true forever. So based on these axioms, this thing is true forever. Okay, and if you assume these things to be true, this thing is true. Okay, this is kind of how it works with math. Okay, once we have proven a thing, this statement is a proposition. Okay, normally there are many ways that we can refer to this kind of true statements. Okay, this is a true statement. And we can also call them lemmas, but you won't see that in this course, and theorem. Okay, so a theorem is a true statement, such like this. So using this properties or any other properties, some assumptions, we arrive to a conclusion that is true forever. And if that conclusion is really important and kind of really useful for math, we call it a theorem. Okay, so you will be able to distinguish the very important statements from the ones that are not that important when we call them theorems. Okay. So yeah, I think that's it. Yeah, and well, this is not a math class, but when it's a math class, but you're not in a math degree. So if you were in a math degree, every proposition that you would be shown in the class, it would have to be accompanied by this proof. Okay, and normally it would be something like that, proof, and then a set of statements, that use these properties to let's say to arrive to the conclusion. Okay, in this case the proof is really easy. Okay, if you use this axioms, you can get to it. So we're not going to deal with it. And when proofs are very complex or not really important, we'll not show them here again, because you're going to be engineers. But in some cases we will deal with proofs so that you get a sense of how these things are arrived at. Okay, and that's the interesting aspect of math, is that I don't need to kind of convince you of that something is true, using kind of being persuasive or being, with a good argument or something. It's that what we do in math is we go from something that's true, then we prove that something else is true, and then we go like this, proving things that are true one after the other until we arrive at our conclusions. And so that's how we know that things will be true forever. Okay, once you've proven a theorem, it stays proven forever. And that's why, in math, the biggest thing that you can do as a mathematician is to prove a big theorem. Okay, and that's the thing that big mathematicians try to do. Okay, so from these axioms, the two axioms, sorry, these 16 axioms from the 10 axioms around the field, and the 16 axioms, sorry, the 6 additional axioms that make a field an ordered field. With these 16 properties, we can actually prove a lot of kind of operation rules that are actually the rules that you use for dealing with real numbers. So you will recognize them from every math course that you have taken before. So this is again a proposition. So this is the and the numbers that come from the sections of the chapters. Okay, so this is the second proposition in this section of the first chapter. So the following properties hold in any ordered field. Okay, and this is what sets up the assumption. So if you say hold in any ordered field, that means you can use all these 16 properties that we have seen before. Okay, so the first one is what we call the unique neutrals. Okay, and so if a plus x equals a for all a, then that means that means that x is a zero, right? This is the property that we've seen before. Okay, this is a number that when you sum it to another number, you get the original number. Well, then x is 0. Okay, it's the same 0 as before. Okay, there are no two zeros for the real numbers. Okay, so if a times x is equal to a, then this x is equal to 1. Okay, so and again, it's important to prove this. Okay, it's not really immediate that these things should be true. Okay? But in general, so if you add any number to another and then this number doesn't change, that number has to be 0, and then if you multiply any number by another number x and the original number doesn't change, then that x has to be 1. Okay, so you can make that known, okay, and use this from now on. Now the second one is that the inverses are unique too. So if a plus x equals to 0, then x is the inverse of a minus a. Okay, there's no other number that has this property. And if a times x equals 1, then x is the inverse of a, so a to the minus 1 or 1 over a if you want. Okay, there's no other number that has this property. Okay. So again, this seemed obvious to you because are the things that you have been using forever, but the important thing to remember is that these things are properties that you can derive using the axioms before, and they depend completely on those axioms. So if you don't have those axioms, you couldn't reach these properties. Okay, so that's very important. That's why I'm spending a lot of time on this, so that you know where all of this comes from. Now 3, that there are no divisors of 0. So if x times y equals 0, then x has to be 0, or y has to be 0, or both of them have to be 0. Okay, there's no way, there's no number that divides 0. Okay. Now 4, cancellation laws for addition. Well, you have a plus x equals b plus x, then a equals b. Okay. And if a plus x is smaller or equal than b plus x, then a is smaller than or equal than b. Okay, we had seen this before. So you can cancel these numbers, and then cancellation law for multiplication. If a times x is equal to b times x, and x is different than 0, this is very important. Okay, then a is equal to b. Okay, if a times x is greater or equal than b times x, then a is greater than b if x is greater than 0 and the sign of the inequality changes. Sorry, the direction of the inequality changes if x is smaller than 0. Okay, so this is very important, please, because everybody makes mistakes on this. Okay, everybody. If this is true, a times x is equal to b times x, and x is 0, then you cannot make any assumption about A and B. Okay, and actually, yeah. So don't do that. Okay, so if then you have anything multiplying by 0, you have to be very careful with that. But if x is different than 0, then you can cancel it out. And when you have inequalities, when you cancel them out, you have to be careful about the sign of the number that you're canceling out. If the number is negative, then the direction of the inequality will change. Okay, and that's super important. And you know, people always fail in exams because of these things. So please, please, please be very careful about this. Okay, 6. 0 times x is 0. It doesn't matter which x you write. Okay, minus x. So the inverse of minus x is x for all x. Minus x, you can write it as minus 1 times x for all x. So if you multiply x by minus 1, you get minus x. And then if x is not 0, then the inverse of x, 1 over x, is not 0. And the inverse of the inverse is x. Okay, so 1 over x is x. Okay. Now 10, if x is different than 0 and y is different than 0, then x times y is not 0. And the inverse is the product of x to the minus 1 times y to the minus 1. Okay? And well, this is important, for instance, when you have matrices. So you will deal with this in linear algebra. When you have matrices, this thing is not true. Okay? And that's because the multiplication for matrices is not commutative. Okay? Because A times B is not B times A in general. Okay? And so the inverse of these products are not the same. Okay, so just remember that. But with real numbers, this is true. Okay, so if x is smaller or equal than y and 0 is smaller or equal than z, so z is a positive number or 0, then x times z is smaller or equal than y times z. Okay, and then if x is smaller or equal than y and z is smaller or equal than 0, then x times z is greater or equal than y times z. Okay, so again, if the number that you're multiplying an inequality with is negative, then the direction of the inequality will change. And then if x is negative, smaller or equal than 0, and y is smaller or equal than 0, then, sorry, this got cut out. X smaller or equal than 0 and y is smaller or equal than 0, then the product will be positive, okay, or 0. And then if x is smaller or equal than 0 and y is greater or equal than 0, then x times y is smaller or equal than 0. Okay? So this is just what you know. If you multiply two negative numbers, you have a positive number, and if you multiply a positive by a negative, you will have a negative number. Okay? Now, 0 is smaller than 1. You can prove it using the axioms directly. And then x squared, so the square of x, so that means x times x. Okay? X times x is greater than 0 for all x. Okay? And well, it's easy to prove this from this. Okay? So if x is positive, then you have positive times positive. We know it's positive. And then if x is negative, it's negative times negative, which is positive again. Okay? And if x is 0, the only way that this is 0 is that x is 0. Okay? So for instance, we can, and now we can start you know, trying to do things with real numbers. Okay, so for instance, we can prove it. Think about you know, prove this thing. So how do we know this is true? Okay, because it doesn't seem obvious. Okay, we are going to use this property 14. Okay, so we start from this statement: a minus b squared is greater or equal than 0. We know that, right? Now we use the distributive law to expand this. We know that this is this. okay, greater than 0. And then we subtract, well, we sum 2 times AB in both sides, okay, and then we divide by 2, or we multiply 1 over 2, and because 2 is a positive number, then the sign of the direction of the inequality doesn't change, and we get here, okay. So you see how we can prove things like that, okay. And then, for instance, we can, so yeah, if you don't know this, these are things that you need to know. A minus b squared, you prove this using this distributive law. So this is just a squared minus ab minus b times a minus b squared, but ab and ba is the same thing because the product is commutative, so this is just minus 2 times ab. And this, if in the case a plus b squared, this is a squared plus 2ab plus b squared, okay. And finally, a plus b times a minus b, so the multiplication of the converse is just a squared plus, minus ab plus ba minus b squared. So this is a squared minus b squared, okay. So these 3 identities are very important, and we will use them throughout the course, so just in case you didn't know them already, they're here for you. So yeah, that's it for now.